Next up is Marko Ivanković, who will be talking about measuring test coverage in none other than Google. So, welcome, Marko.
Okay, cool. Thanks. Hello, everyone. Welcome. I'm happy to see so many faces after the lunch break. That's nice. So my name is Marko Ivanković. I work in Google as a software engineer in test. And today I want to talk to you a little bit about measuring test coverage. And short agenda and introduction. I want to give you a little bit of a background to help you understand the results that we gain and how to interpret them. I want to show you what exactly we mean when we say test coverage. And the total time to do this is going to be 20 minutes, like all the other presentations, and another 5 minutes for Q&A. Right, so let's start. Google, one word. One company, maybe externally, but actually, we're talking about hundreds of products. We're talking about thousands of engineers. We're talking about offices around the world. And most importantly, we're talking about millions of lines of code. Right. So, some of you might already know this. For some of you, this might be new. These millions of lines of code live in one single repository. There are small, well, maybe not so small, exceptions like Chrome and Android, because they are open source and then they have their own open source repositories. But the rest of the code lives in this gigantic repository spanning millions of lines of code, which is accessible to every single engineer. We do not use branching. Development is done against head. So there is one single source of information. You can ask what the code base looks like now, at this moment, and you can get it. And the answer is the same for every engineer. You don't have your own local Git branch that diverges significantly from the rest of the code base. This has certain implications, of course. This repository has many languages in it. The code is not separated in any artificial way. There are sort of natural separations that projects tend to be written in one, maybe two languages. But in general, the repository itself contains many languages. And of maybe even all languages, you never know. But the big ones are C++, Java, Python, Go, and JavaScript. And this is important because everything I say here today probably applies for these 5 languages. I can't say whether or not it applies for others because we don't have a significant code base. Right. We are also talking about thousands of code changes per day. And this means all day. Because the offices are spanned around the globe. When you're asleep, somebody somewhere is coding, checking your code. And the changes happen from core libraries. There's people working on string.h and stuff like that, to people working on their small button somewhere in Gmail. Right. And another question people then ask very often is this broken all the time, or just most of the time? And the surprising answer is that the code base is mostly helping. So most of the time you should be able to check out any bit of the code base, compile it, all the tests should pass, it should work. And the reason why this is mostly helping is because we invested a lot of time and a lot of effort in automating almost the entire development process. And it all revolves around the central concept of a code review. Now, any bit of code, before it is checked into this central repository, has to be reviewed. The review is usually done by another engineer on the team. It's a somewhat informal process. And you're supposed to do small incremental changes. The process is supposed to be efficient. And it is all done through a centralized web-based interface, which allows for efficient communication. Everybody knows exactly everybody knows exactly which kind of UI everybody else has, so you can sort of communicate efficiently and reason about it. And it is mandatory, so there is no way you can check in code without going through this process. And because it is mandatory, it is the very best place where we can do automated analysis, because we can look at every bit of code that goes in, as it goes in, and sort of enforce certain properties. For example, you can enforce that before the code is checked in, it doesn't break any tests. So you know, if I do this commit, if I do this push, will it break any tests? You know this before you do it. At this point, we also do something which is called style guide compliance enforcement, which is basically a fancy way of saying, are you using the language correctly? So we do sort of static analysis, that you're not doing anything that could be potentially dangerous from a language perspective. And this is the place where we actually plug in test coverage. This is where this coverage information means the most. The thing about this is, all these tools have to be really fast. Typically, a code review response time is 2 to 4 hours. Right? So it's essentially you're shooting an email to another engineer, and within 4 hours this process will be finished. You will agree whether or not this code is good. Right. As part of this code review process, there is a definite human element. So another engineer has to approve 2 specific things. They need to approve, if you do not work on this project, if you don't own the code, someone who does needs to approve this commit, needs to approve this code change and say, yes, this makes sense for our project. And this style guide enforcement is also done partially by humans, because some of the sort of more advanced things can't be really done by static analysis. So an engineer that has previously shown really good skills with, for example, Python, would look at your Python code and say, yeah, this is good Python code, this makes sense. And the important bit is that these reviewers also see the results of any automated analysis that goes around. So this is completely transparent. So usually during the review process, the reviewer also has to say whether or not you've done enough testing. Generally, within the company, we agree that every code should be accompanied by testing. And this is reasonably easy to automatically check. You can just see whether or not a test exists. But how much testing, though? Now that's a difficult question to answer, right? Because maybe there is this error path that you don't necessarily care about it. You have it in your code so that it doesn't crash, or so that you avoid some other really harmful effect, but all you do there is just log or discard results or so on. And okay, maybe necessarily you don't need to test that. But how do you decide whether or not that's true? Turns out that doing that automatically is really, really difficult. However, a human can do that reasonably fast. An engineer, when you look at a piece of code, if you've been working on this project, you're reasonably good at saying maybe this piece of code doesn't need to be tested, or this piece of code should be tested. However, humans are really bad at determining is this piece of code tested. Because usually the tests are written in a separate file, maybe you need to go line by line, okay, so I'm tracking this variable, was it good, was it, okay. But this bit, we can assist by tools. What we can do is, we can easily measure how much the tests exercise the code. This can be done automatically. And in general, in sort of theory, there are many ways of doing this, which then specify many ways, types of coverage. Here they are ordered roughly in their resolution, how good they, on what size of code they operate, and in the complexity of calculating them. So the function coverage is basically, for each function, was this function called? It doesn't matter what the parameters were, it doesn't matter which test did it, was it called or not? That's reasonably simple to calculate. You can just add a logging under each function definition and then check the logs. If the log statement is there, if it was executed, right, that function is covered. Statement coverage, same idea, line of code. Obviously this gives you better resolution because a function can be 10, 20 lines with ifs, and conditions and loops and so on. A single line, much better resolution, more difficult to calculate them. Branch coverage, here you're asking, okay, if I have an if, which has 5 different conditionals, was each and every one of them actually true during the testing? Or was it something like if true, and then this super complex thing that never actually gets tested? Again, this gives you, because it's all in the same line, right? This gives you a little bit better resolution, but it's even more complex. And then you can go further and further and further, but they become increasingly expensive to calculate. And we have found that on a very large sample of data, we have confirmed that it's enough to look at statement coverage for most parts. You really don't need to bother with the rest. There is not necessarily good correlation between statement and branch coverage itself, but correlation between anything else is usually exactly the same. So if you plan to measure coverage at any point, and somebody tells you, well, which one, just tell them statement. It's going to be good enough. So how do we exactly do this? Well, we measure it per project, where a project is basically defined by a group of people working on one task for a long amount of time, and they own certain small bits of this huge repository. There can be some overlap here. A piece of code can be sort of part of more than one project, but then we just calculate it twice. And we do this once per day for all the projects. Now, for each commit, during the code review, we calculate code coverage at least once. Sometimes more than once, sometimes a lot more than once. And we do this as part of the code review process. So, although we do a lot of research on coverage, there's also a lot of engineering to show this data and to use it when it's needed in a way that makes the most sense. And in doing this, we have collected about 1.5 years worth of data across hundreds of projects, and this is across hundreds of thousands of commits, or batches. Actually, the number is millions of commits, but in some of the charts and the results that I'm going to show you, we couldn't use all of them, because, for example, when I talk about specific language, not all commits had all languages. But yeah, so we're talking about roughly 1,000 projects and a few million commits. Right. And this is actually how coverage looks like. This is a histogram of coverage. Each line on the x-axis represents coverage, and this is the number of projects that has this specific coverage at the time where I did this chart. And it's, I think, aggregated over 1 month. To sort of help you reason about it, half of the projects have 78% coverage or more. 75th percentile, 85% coverage the top 10% of the project have 90% of their code base covered in a way that we can measure. Now here's an interesting bit though. If you go and split this by language, you get a very, very different picture. C++, on average, a little bit about, I think it's 56%. Java does a little bit better. Java gets it over 60. Go, okay, the code base is a little bit better, 65. But JavaScript and Python, they just go way up.